Our last gas video today for your review will be on effusion and diffusion of gases. And that was the last thing we studied in class, and it's hopefully fairly easy. Graham's law of effusion can be easily derived from the expression for velocity for gases. And we know that the speed is inversely proportional to the square root of the molar mass. So bigger things move more slowly. Effusion is the movement of gas through a very small hole into an evacuated chamber. And this is a diagram. And it's going to do that at a certain rate depending upon its molar mass. And we oftentimes compare two gases, and we do that so that we can get the molar mass of an unknown gas. So it says here, gas particles that move faster will effuse at a faster rate. That's sort of axiomatic, I guess. Gas particles with smaller molar masses have higher average velocities. We saw that in the last video. Than do gases with larger molar masses at the same temperature. So we have Graham's law of effusion. The rate of gas 1 divided by the rate of effusion of gas 2 is equal to the square root of the molar mass of gas 2 divided by the molar mass of gas 1. So if you're just looking at two gases, for example, you can find the ratio of the rates. And this is saying that, hey, if I look at the ratio of the rates of helium and neon here, helium goes about 2.25 times faster than neon when effusing through a hole. Diffusion is the bulk movement of one type of gas into another. So we have a situation like that where eventually you're going to have some sort of equilibrium. Okay, let's take a look here. This is an example of using the same idea for diffusion rates. A sample of an unknown gas diffuses 3 times faster than butane. What is the molar mass of the unknown gas? Now, we don't have any rates here. All we know is this gas goes 3 times faster than butane. Butane is, 58 grams per mole. So this is going to have a molar mass less than that. And the way I got the 58 grams per mole, you know how to do that. I know some people still get frightened when I just throw that out there. You just take 4 times 12 for the carbon plus 10 for the hydrogen and add them up. Molar mass. Okay, so you set it up this way. On the board I was calling it like the rate of X divided by the molar, and then I have the molar mass of X here. They just put a question mark. You can write it any way you like. So, but if you just say, hey, this rate is 3 times the rate of butane, then you could have like 3x over X or whatever, and then the bottom line is we don't need the rate because it's just going to cancel out. We just need the factor of 3 here. So we square both sides and go ahead and solve for the molar mass again. This is in the denominator, so it's going to swap places with the 3 squared. And we're going to see that our molar mass is about 6.46 grams per mole, which is just kind of silly because I can't think of a gas with that molar mass, but it doesn't matter. These problems are just set up so you get an answer. And that's pretty much all I want to go through with you. It's just some examples of things. And finally, if you talk about a real gas is under high pressure and low temperatures, they differ in behavior from ideal gases. Ideal gases had PV equals nRT, but we have to take into account when these gas molecules start getting closer to each other at high pressures and low temperatures, we have to take into account things like intermolecular forces of attraction and actually the size of the gas molecules at that point. But there's an equation that describes it. It's called the van der Waals equation, and I did not go over that in class, so you are not responsible for it. Have a good day. Don't worry too much about the test. I think it should be straightforward. If you have any questions, email me.